All right, this is the video for chapter 5.1 and 5.2, talking about linear functions, identifying them. So first, let's identify what a linear function is. A linear function is a function that has a constant rate of change. And forms a straight line on the graph. Okay, so two key things there: constant rate of change and a straight line on a graph. So if I take a look at these three graphs, I can pretty easily tell which one's a linear function. Now, keep in mind what a function is. A function is a relation where each input has exactly one output. So it has to be a function in order to be a linear function. So this first one, it is a linear function because it is a straight line on the graph. So is the second one because it is a straight line, and this is a function. Okay, this is a function. A horizontal line is a function. This is not a linear function because it is not a straight line. It is a curved line. In fact, it's actually not even a function at all because it does not pass the vertical line test. So it's not a function, but if it were a function, it would not be linear. All right, now let's look at from a table, how do we identify if it's linear or not? Well, this is where we need to look at the rate of change. We want to specifically look at the change in y versus the change in x. Delta, this delta sign means change. So all I'm going to do here is I'm going to figure out the pattern, if there is one. So how do I get from 7 to 4? I'm minus 3. From 4 to 1, minus 3. From 1 to negative 2, minus 3. So this looks like it's a constant rate, but in order to really determine that, we have to make sure the x's are also going by the same pattern. Not necessarily negative 3, but that it's consistent. So this is plus 1, plus 1, plus 1, and plus 1. So the rate of change here is negative 3 over 1. And it's consistent all the time. So that is a linear function. All right, let's look at this one down here. From 6 to 3 is minus 3. From 3 to 2 is minus 1. So because these are different, I can stop. Let me go look at these and see if they're the same or different. Negative 2 to negative 1 is plus 1. Negative 1 to 0 is plus 1. So look, these are different, but these are the same. So in this example, the rate of change is negative 3 over 1. But in this example, the rate of change is negative 1 over 1. Those are not equal, so the rate of change is not constant, so it is not linear. Is it a function? Yes, because the inputs don't repeat, but it is not a linear function. All right, last table over here. Negative 6 to negative 5 is plus 1. Negative 5 to negative 4 is plus 1. And negative 4 to negative 2 is plus 2. So this is interesting. These are the same, but this is different. So we got to make sure we pay attention to that. This is plus 2, and plus 4. Interesting. So these are 1 over 2. Both of these, 1 over 2. Change in y over change in x. And this one is 2 over 4. So is that a constant rate of change? Well, yes it is, because 1/2 is the same as 2 over 4. So the table just happened to skip here. So instead of just adding 1, adding 1, this time it added 2. So it kind of skipped a value here that we were counting on. But that doesn't mean that it's not linear. So this one is linear. So the ratios have to be equal. They don't have to be exactly the same, they just have to be equal. Well, by exactly the same, I mean it doesn't always have to be 1 over 2, because 2 over 4 is the same as 1 over 2. Right now when we look at ordered pairs, you can kind of do this a couple ways. Honestly, I like to just put it in a table. So I just say 2, 4, 5, 3, 8, 2, 11, 1. So from 4 to 3 is minus 1, minus 1, minus 1, plus 3, plus 3, plus 3. So it stays the same throughout. The rate of change is -1 over 3. Okay, so again, rate of change is the change in y over the change in x. All right, so now let's look at from an equation. How do we determine if it is linear from an equation? Well, the first thing we need to look at is what is the standard form of a linear function? Standard form is ax plus by equals c. A and b cannot equal 0. Okay, that is standard form. If a and b equals 0, then it's not linear. Okay, so some examples of linear. For example, 3x plus 8y equals 2. So this looks very similar to this. This. A, B, and C are just numbers. Okay, but again, A and B are not 0. So A, B, and C are just numbers. So 3x plus 8y equals 2, that is linear. Another example of a linear function would be y equals 1/2 x minus 4. Because I could move this to the other side and it would look like this. And then y minus 2 equals 3x. Again, I can move the 3x over and move the minus 2 over, and it would look like standard form. Ax plus by equals c. So these are all examples of linear functions. Nonlinear functions, okay, so there's 3 main things that can't happen for it to be linear. The first thing is we cannot have the x or y in the denominator. So this is not linear because the x is in the denominator. That's the problem there. All right. The next thing is the x and y have to be to the first power. So here we have x squared. So x is raised to a power other than 1. That is not okay. So again, that is not linear. And then the last example is the x and the y cannot be multiplied by each other. So those are examples of linear versus nonlinear. These are the things you're looking for. If an equation has one of these 3 things, then you know that it is not a linear function. Remember, these are linear, so they are going to be straight lines on a graph. All right, now let's talk about what are called our intercepts, the x and y intercept. The x-intercept is the x value when y equals 0. And it's written as x comma 0. So whatever the x value is, but the y value will be 0. It's also where the function, abbreviate function here, crosses the x-axis. The y-intercept is the y value when x equals 0. So it is written as 0 comma y. And it's where the function crosses the y-axis. Okay, so x-intercept and y-intercept. So let's identify intercepts from a graph. So when we're looking at a graph, we want to look at where does the function cross the x or the y-axis. Okay, remember this is the y-axis and the x-axis is here. So the x-intercept in this problem is -5. Okay, it crosses here at -5. So we would write that as -5, comma 0. That's this point here. And the y-intercept is 1. So we write that as 0, 1. Here, the x-intercept is 2, so 2, 0. And the y-intercept is 0, -4. Last one, the y-intercept is -3. And the x-intercept is -2. It's very important that your zeros are in the correct place. Okay, so identify where the function crosses the x or y axis, and then just identify the coordinate point. Points on the x-axis have a y value of 0. Points on the y-axis have an x value of 0. That's always true. All right, now we're going to identify intercepts from an equation. So when we're looking at the equations, we want to remember this part. It's the x value when y equals 0. So if I want to find the x-intercept, here, then I need to plug in a 0 for y. Okay, so that would look like 3x minus 2 times 0 equals 9. Well, guess what? -2 times 0 is nothing. So I really can just cover that up. I can just cross that out. Now I divide by 3, x equals 3. So that would be 3, comma 0. You must remember that the x and y intercept are coordinate points. Okay, so if I ask for the x-intercept, this is what I'm looking for. Now let's do the y-intercept. So the y-intercept is going to be when x equals 0. So 3 times 0 minus 2y equals 9. Again, 3 times 0 is nothing. So now I divide by -2 because they're being multiplied. So y equals -9 over 2. So 0, comma -9 over 2, which you should know is 4.5, -4.5. That way you would know where it would fall on the graph. All right, let's do this one here. Y-intercepts, or let's see, no, x-intercept. -3x plus 5 times 0 equals 30. Cover this up, right? That's gone. Divide by -3. X equals -10, so I write that as -10, comma 0. And then -3 times 0 plus 5y equals 30. That goes away. Divide by 5. Y equals 6. So 0, 6. So now, if you needed to, you could graph this function, this linear function, using these 2 points. And that is what we're going to look at next. Okay, so we have this function. This is in standard form. It is a linear function. So I want to find the intercepts. That way I can graph it. So I can have 2 points to make a line. So let's do my x-intercept first. 3x minus 2 times 0 equals 12. Divide by 3. X equals 4. So that's 4, comma 0. So I'm going to go ahead and plot that point right here. That's 1 point. Now I'm going to do my y-intercept. 3 times 0 minus 2y equals 12. This goes away. Divide by -2. Y equals -6. So that is 0, -6. 0, -6. Now I can make my line. Please use a straight edge when you are making lines. Okay, and you can extend that line. You know, it doesn't have to, it shouldn't just go from here to here. It shouldn't stop at these 2 points. It should go through those 2 points and extend. Notice that my line has arrows on the end of it. So that's how you graph that line using the intercepts. All right, so now this one is not in standard form. So what we're actually going to do first is we are going to rewrite this in standard form. So it says y equals 1/3 x minus 2. This is linear, okay? The x is not in the denominator. This is a linear function. So in order to put this in standard form, remember standard form is ax plus by equals c. So I want my x and y on the left side, and I really would prefer whole numbers. So I want to get rid of this 1/3. How do I get rid of the 1/3? I multiply by the reciprocal. So I'm going to multiply by 3 there and 3 here. So I get 3y equals, now you have to distribute the 3, okay? So 3 times 1/3 is 1, so that's x. 3 times -2 is -6. Now I want the x on the other side, so I'm going to subtract x and get 3y minus x equals -6. Now I can cover up. I can use my cover up method. Okay, so I'm going to show you that. All right, so I'm going to cover up my y to find my x intercept. So to find x, I cover this up, and all I have to do is divide by -1. So x equals 6. So that's my x-intercept. And then to find my y-intercept, I cover up my x and solve for y. Divide by 3. Divide by 3, y equals -2. Oh, that's not a -2. So -2 here. And now I can draw my line. Remember, your line should extend through the 2 points. It should not just stop at the 2 points. There we go. All right. So that is how you graph using the intercept. So we want to be in standard form in order to more easily graph it using the intercepts, okay? You could have plugged in a 0 for this x to find the y-intercept and a 0 for y to find the x-intercept, but I want you to see how to put this into standard form and then just use your cover-up method to find the 2 intercepts, okay? Please go back and rewatch parts of this video that you didn't understand, and be ready to ask your questions in class. See you then.